He's a professor of psychology. Professor Ullman leads the Computation, Cognition, and Development Lab over at Harvard, where he focuses on intuitive theories and human common sense reasoning on physics and psychology. When I first came across Professor Ullman's work, it was at the very start of my PhD, and I saw a paper titled "A Minimal Turing Test." I won't give away all of it because it's a fun read, but I'll say it takes this idea of a Turing test, the Alan Turing imitation game, and says, what would people do if they could only answer with one word? And what you'll find if you take a read is it will make you laugh and then make you think. And I think a lot of Tomer's work really makes me think deeply about who we are as people and how we learn and how we think about the world. So he's super well published. He's really a visionary and pioneer in interdisciplinary spaces from AI to developmental psychology to cognitive science. He publishes in all of those spaces. So that's NeurIPS, there's developmental psychology journals, Trends in Cognitive Sciences, Brain and Behavioral Science, and what else do I want to say? The last thing I'll say is he has a really cool, I don't think he's going to talk about this today, but a paper that I really liked from last year was the illusion. And so the idea there was looking at classic illusions that humans experience and seeing how if you make minor perturbations that no human would then still see it as an illusion, AI systems see these things as illusions. So he has really creative ideas about how you can probe AI and human systems to understand the differences and how we actually see the world. So without further ado, Tomer Ullman, take it away.
Thank you so much for that very kind introduction, and thank you so much for having me here. I really appreciate the invitation and the opportunity to speak to all of you. I know that this is a very diverse crowd, and that makes sense given the topics that you're interested in. Can people, by the way, hear me okay? Is this great? Okay, seeing some thumbs up, appreciate it. All right, so as the title says, today we'll be talking about good enough approximations in mental simulation and intuitive physics. And the way that this is going to work is that first I'm going to talk a little bit about what's my deal, what's your deal, my deal. You meaning me meaning, I really shouldn't have given up on my speaker notes, but okay. So we already heard from the introduction a little bit of what I'm interested in. I want to spend just a minute or two kind of solidifying that, what it is that I study, why I study it, and things like that. And then I'll make it a bit more specific because as you heard, I'm interested in intuitive theories and common sense. I don't have time to talk about all of that today, thankfully. I want to focus specifically about one branch of research, intuitive physics. But I need to do some setup to tell you about the latest work that I'm really excited about, right? To get you to that point, I need to do a little bit of setup of what we know that's come way before me, right? Stuff that we know in cognitive science, we still need to find common ground there. But then I'll tell you a little bit about some recent projects, including approximate bodies, partial simulation, and then we'll move to things like non-commitment and capacity limits, which have to do with intuitive physics, but this is where intuitive physics meets the imagination and imagery. And it might be obvious to you that these two things are related, but the research has not actually been that overlapping in some ways, but this is. A side note before we get into what's my deal, I know I tend to talk a little bit fast, and there's a bunch of stuff that I put up here, and I also heard that people will ask questions in the middle, and that's okay. So please feel free to raise your hand and ask questions and things like that. I, however, reserve the right to sometimes say, that's a great question, let's come back to that in the discussion. Because what I'm going to do here in these things is go a bit quickly. The assumption is you can go and read the paper to find out things like what ages was it? And did you control for that? Like these kind of things I'm happy to talk about, but I might say for that you can read the paper. I'm trying to get across a more general idea here, okay? And I'm trying to get that idea across through these papers, so I might talk about them a little bit quickly and then have a more open discussion, if that's okay. Okay, and with that in mind, what's your deal, you meaning me? So as you heard, I run the Computation, Cognition, Development Lab, which is what it says on the tin. I'm interested in computation, cognition, and development. I'm interested in people's common sense reasoning, right? The things that we all kind of do intuitively. And what do we mean exactly by intuitive is stuff I've certainly thought a lot about. But for example, it's the thing about intuitive physics, which is people, I know there are physicists in the audience, but it's non-physicists can also reason about what would happen if I suddenly smack this way, right? Or threw it towards you, or I'm not gonna do it, don't worry. So if I suddenly threw it in a certain way, you'd have something in your mind, that would allow you to reason about that. You can do some sort of prediction, some sort of inference. If it didn't go the way you expected, it floated into the air, it smashed into a billion pieces, you would be surprised by that. So you can do prediction, counterfactual reasoning, things like that about physics. And I put it to you that you can do that as a non-physicist. And who's a physicist, by the way? Raise your hand if you don't mind. Okay. I put it to you that even you physicists are not doing physics in the sense that you're thinking about it when you're solving that kind of task. Okay. But what are you doing, right, is super interesting. And then there's also intuitive psychology, which I won't have time to talk about too much today. But again, if I were to do that, I'm not going to do it. But if I were to do it, you would also probably, not just the physics, you would be like, oh, that's interesting. It must weigh about 300 grams. You'd probably be thinking, what the hell is he doing? What's wrong with this person? You'd be wondering about my mental states and emotions and things like that. And again, how many of you are cognitive scientists or psychologists? Okay, great. I put it to you that you're not using your hard-earned knowledge to reason about that. We're all doing that intuitively and quickly and things like that, reasoning about other people's mental states. I'm interested in studying these kind of theories through childhood up to adulthood, because I think that children are interestingly similar and interestingly different when it comes to this kind of reasoning. And I'm interested in building computational models of all this kind of thing, because I feel if we don't have a computational model, this kind of stuff, I feel like we don't quite understand what is going on, and that leads me to naturally try and compare this to AI and things like that. It's not that I'm so hot on robots per se, I just think that they're an interesting comparison to what it is that people are doing. If that tickles you, if you have questions and things like that, I encourage you to read this piece where it's kind of laid out a bit more in depth and things like that. Okay, so that's my deal. Let's dive into intuitive physics from babies to adults. Okay, and sorry, I'm going to turn this over here because I want to make sure I'm keeping time. Okay. Here's an idea that I think is important to put on the table before we get to what's next. This is not my original idea. I'm just working within this framework, but I think it's important to know what this is. When I say core knowledge, how many people know what I'm talking about? We're doing a bit of call and response. Okay, seeing some people. How many people don't know what I'm talking about? That's okay. Great, there's a reason the slide exists. Wonderful. So core knowledge is this idea that's been coming out of development. It's hard to say that like developmentalists agree on anything. That would be weird, right? Like if you ever heard someone say philosophers think that, you know not to trust that person, right? Like in the same way, you can't say like psychologists know that or developmentalists agree that. So, but this is a very important idea in cognitive development that many people do work within and agree with. The idea is that children are not tabula rasa when they're born into the world, and they don't know everything about everything. They know some things about some things, about a limited number of, a core number of domains. They have this kind of early knowledge, early understanding that's either early developing or possibly innate. This kind of reasoning is the kind of stuff that Darwin would put into animals, right? Like as well. Humans are not the first species to have to deal with mental states and physics. It makes sense that it is shared with other animals. It is about a small number of domains, specifically agents, objects, space, number, and depending on when you talk to Liz Spelke that morning, maybe social stuff as well. So again, general principles, limited domains. What do I mean by that? Hopefully that's created some kind of understanding, but not, I'm sure a lot of you are like, okay, can you give us an example? Yes, I can. So let's focus specifically about this idea of core knowledge when it comes to core physics, okay? So the idea is that infants have these early expectations, even infants, I should say, have early expectations about objects. This is hopefully not too surprising to you, but if you are surprised, you should know that the way we study that is through surprising people and surprising infants. That's one way of studying it. So one thing that we might do, for example, is we show people displays that are like this, but realistic, okay? So suppose that you're a baby now in this study and you're seeing the cylinder. And the cylinder is going to move, and then I have a question for you, okay? So get ready. There's going to be some audience participation here. So here we go. Cylinder is moving. It's a baby experiment. There's fun music. There we go. Okay. And my question, and then you see it multiple times because you're a baby and you don't have good memory. And my question to you is, are there two objects in this scene or one? Who thinks that there's one cylinder in this scene? Who thinks that there are two cylinders in this scene? Who thinks this is a PowerPoint presentation? Who knows what's going on? Okay. And we could, I could just ask you, I could query you as adults. What I could do with children is I could take these these occluders away, and then those of you who said two objects are hopefully surprised. Where's the other cylinder? Where did it go, right? So we can do that kind of thing. There's many other ways of testing this. Here's so that would be an example of like testing children's understanding of permanence. Here's an example of testing children's understanding of solidity, okay? So watch that. Right, here's the occluder, it's coming over. This isn't surprising that it disappeared from view, okay? It's not about the object disappearing from view. Oh my God, what happened to Teddy, right? That's the problem, that it's a violation of solidity, okay? And hopefully you got that tingle of that's kind of weird. The idea is that from early on, humans have these kind of fundamental expectations about the behavior of other objects qua them being objects. It's not that they have to relearn it for cylinders and then relearn it for teddy bears or something like that. This thing as a physical object should be permanent, coherent, obey solidity, follow smooth paths, and things like that. Okay. So with that in mind, right, okay, so this is very early developing and things like that, but children are not adults, spoiler alert. I don't know why that's, anyway, okay. Children are not adult, as research shows, but adults also have this sense of intuitive physics, but it's a bit more refined than children. Adults are also able to reason about the ways that things bounce and things drape and things smash and things collide and things goop and oop and other terms that I've invented and things like that. The idea is, again, as I said with a mug, at first that you can reason about the way that these things move, you can predict how they'll move, you can run inferences on these and things like that. And the question for both the developmental thing and the adults is how? Okay, so in the same way that it turned out to be a billion-trillion-dollar industry to look at, what is this, by the way? This isn't a trick question. 1, 2, 3, what is this? Thank you, okay. How do you know it's a mug, right? Like that question might be, that might seem nonsensical to you as a question, like I look at it and I see it's a mug, what do you mean? And the point is that you don't exactly know how you're doing it, and even those of you who are like, well, you see the information comes to the retina and then it goes to V1 and things like that, like fine, you took a class, you didn't roll your eyes backward and figure that out, right? Like it took a lot of work to figure out what are the computations that go from the image of this thing to the statement mug. In the same way I put it to you, it's interesting to study and interesting to consider what are the computations that go from you seeing these images to you being able to reason about this stuff. This is trivially easy, intuitive, obvious, and yet really hard, actually. Because when we try to build models of these things, they turn out to not be trivial, okay? And the question for us, people who are interested in this kind of stuff, is what are these computations, and can you give a story that takes you from development all the way to adulthood? And one very powerful story, not the only one, definitely contentious, as I hope to show you in this talk today, is the idea that maybe people are running something like a mental simulation, okay? That supports a lot of their reasoning. The same software that was used to create these scenes, even though these scenes are visually very different from one another, they were created by the same underlying computations, the same underlying program. The argument is maybe we're running something kind of like that program. And that program is very useful, even if you didn't know anything empirically about whether or not people are doing this. I put it to you that if you're just an engineer building an organism, I put it to you that it would be, it would be great to put this kind of thing in your organism. Because if you have something like this mental simulation, this kind of program, then you can use that program to fix certain variables in that program. If you know the ball is over here and it's this heavy and it's moving at this speed, you can predict what will happen next. But if you have this kind of probabilistic program, you can also condition on the observations you have and run inference, like the ball surprised you, it must be lighter than you expected. And you can generalize to new scenarios that don't visually look like the scenarios that you've seen before. And also, this thing is, this kind of mental engine program is not the only game in town, not in terms of cognitive science, not in terms of development, and also not in terms of how current frontier AI companies are trying to build stuff, okay? So I'm sure a lot of you are familiar with these kind of video generation models like VO3 or Sora 2 or Bumblestick 7 or whatever came out since this morning, I haven't checked. But those things are not running a game engine under the hood, and it shows. Okay, so this is like the latest and greatest, thousands of PhD years, $1 trillion spent on showing this initial thing and saying this car is running into a wall, please generate the next few scenes of the thing. Okay, so that was me trying it like on the most recent thing. There's a lot of stuff that you can do about permanence and solidity and cohesion and things like that, but it just doesn't work that well even across a few seconds, and it's maybe not surprising. All right, as I said, all of that is kind of groundwork for what's coming next, okay? This stuff is not too contentious from what I'm saying so far. Again, part of what I'm saying is also that there exists contention, so that part isn't contentious. The fact is this kind of phenomena exists. People are able to reason about that stuff. That's not a discussion. One possible explanation for this is that people are running something like this game engine mental simulation. It's not under discussion that that proposal is out there. It's not a discussion that it has its detractors. What I want to talk to you about today is this notion of good enough, okay? So take all of that on board for a moment. And the topic for today is approximations in these game engines, okay? If people have something like this mental game engine that they're using to reason about physics in this way, what kind of mental simulation is it, right? It can't be perfect. You can't be, when people are trying to, for example, if I'm a video game designer or something like that, I'm trying to capture this in like Grand Theft Auto or whatever people are playing these days, I don't know. My kids play stuff. Zelda Breath of the Wild, that's out of date as well. Okay, so if I'm trying to capture that, I'm not gonna simulate it at a molecular level, shout out to physicists, okay, at a quantum level. I'm gonna simulate it at the level of approximate bodies. I'm gonna do all sorts of hacks, principled hacks, okay? There's reasons why I'm using these things because I need to get around these constraints of time and memory and computation to produce something that looks good enough as an engineer, okay? And the idea is, well, that's really interesting because the kind of stuff that people have come up for machines are maybe the kind of constraints that our mind needs to get around as well. Our mind is also finite, sorry to say, right? We also have constraints of memory and time and computation, things like that. So maybe we can take these ideas of approximations that people have come up with for generating a world that is good enough in machines as kind of first level hypotheses, starting hypotheses for how the mind might be approximating the simulation. And that's what I want to talk to you about today. This, I feel, has been really fruitful as a working hypothesis for intuitive physics. And if you want to know more, Starship Troopers reference for the older people in the audience, there's a lot of papers on this kind of thing. I mean, there's a lot beyond those as well, but go ahead and read those if you like coming up. These are all out of the lab in the last few years. But within those, I'm going to focus on 4 ones that I find particularly interesting and cool. They're all my children. I love all of them, but I think these are interesting to think about for various reasons. Okay, great. So that's set up. Here we go. Let's talk about the particular papers with that in mind. The first thing is this relatively simple approximation that nevertheless I think is really cool, and you see it all over the place. It doesn't matter if the game engine that you're using as an engineer is, I don't know how many people play with game engines, but like if you're using Unity or Blender or Unreal or whatever it is, a 2D, 3D engine, there's this repeating idea of you have to have object simplifications, okay? That if I were to simulate this thing being thrown across the room and hitting it, I don't necessarily care about the particular kink of this angle, okay? Or maybe a different, here, what's this? Let's think about this object for a second, right? For purposes of visual recognition and displaying what it looks like in the game, it's really important that this thing is kind of shiny over here and has this nice like ergonomic curvature and blah, blah, blah. But if I just throw it at the wall, that's a waste of time, right? Like we should probably just approximate this with the convex hull or a cylinder or a bounding box or something like that. Again, that's been a very fruitful idea that's been showing up again and again. And in real systems that are meant to simulate stuff. The question for us then is, okay, if this is what we're seeing visually, under the hood, are we using these kind of physical approximations when we're reasoning about how things smash and crash and when we're trying to track them? And if we are using this kind of approximation, is it more like that? Or is it more like that, right? Where in this kind of approximation are we? All right, and this, I want to give a shout out to Yichen Li, who was the student who led this work. So again, this idea is that let's separate between the shape, which contains the fine-grained information for rendering something onto the screen, or in the case of humans, recognizing visually what this thing is as an object, and separate that from the body, right? The thing that is used for physical tracking and determining where things are and are they about to collide and what happens when they collide. And you would use approximations for that. These things are rendered, fine-grained, and care about texture and things like that. These things do not, okay? Yes.
Cube and not a sphere. As a physicist, I'm always thinking the final approximation is a sphere. Is it because of pixels? And
do you mean why do engineers use cubes, or do you mean why might people, cognitively speaking, use a cube as opposed to a sphere approximation? Both. Okay. For engineers, I'm going to punt it because I'm not an engineer. There are many possible approximations that people use as well and reasons why they do it, and I'm going to just plead ignorance for now. For people, I want to leave it open, right? The question was, do people use this approximation? And if they do, does it look more like that, or more like a sphere, or more like this kind of thing? Important, empirical question. And the answer, by the way, is that they use it depending on, well, all right. It depends a little bit how many resources they have, by the way, as well, which I think is important for people as well. So what we need, and then thank you, by the way, for that question. So what we need is tests that dissociate what I was calling the body from the shape. And we can come up with a bunch of them, but for all of them, they're going to have this repeating kind of idea where suppose that these are always going to be the shape, right? The shape, you can visually recognize these things, obviously. We were using, those of you who know it, we're using Cooper shapes, which are meant to be like non-verbalizable. I'm sure you can think of things that these look like, but the point is you probably won't agree on what they look like, okay? And the question is like, are people using, if we can imagine some kind of approximation, which approximation is it? Let's imagine the approximation is kind of like a shrink wrap, right? Is it more like this? And then we can imagine like all the way over here, right? So we need something that distinguishes that kind of thing to, okay, greater body approximations in this way. So in all these cases, the distance between these two objects is the same, between the two shapes, the two real things, the distance is the same, but it's a different distance in terms of the effective distance if you're using different approximations. Do people see that? Right? Like the difference between these two approximations is they're basically touching one another. Great, so we can use that in a bunch of different ways. So I'm going to show you a particular task that then tries to get at this idea, that uses what we know already about how people see collisions to try and get at this idea. Okay. How many people know the Michaud-ian launching task? Great. How many people don't know the Michaud-ian launching task? There was a clear correlation between that and core knowledge as well, so yeah, not surprising. So Michaud-ian launching is a very old, very, very old task in cognitive science. It in fact predates the term cognitive science, and it has to do with causality. I'm not going to get into it too much, but the point is that this has been studied in a bazillion different studies, and it always involves an agent object moving towards a patient object and then stopping. Let me just show you what it looks like. Okay, so watch this. There's an agent, and it hits the patient is my interpretation, but it moves and it stops moving, and then that thing moves. Okay, so that's what I mean. And this is run a lot more smoothly on the machines that people see because they're not on Zoom and things like that. But please imagine this running smoothly or something like that. My question to you as a participant in this study is, did the agent cause the patient to move? Okay, and what I'd like you to just raise your hand. This is like definitely yes, 7 out of 7. This is definitely no, 1 out of 7. Okay, so the question is, did the agent cause the patient to move? Let's see that video again. All right, okay, so yeah, you're participants in this study. It's a 4.75, I'd say, or something along those lines. All right. Now, again, this is incredibly well studied, right? And the idea is that when people see this, they're pretty likely to say that this caused that to move. When they see this, they're much less likely to say it. And when they see this, they're less likely to say it. So the distance between the objects, there's a particular function of their causality ratings and how it drops off. But what if the distance is now different because we're using this approximation? Visually, it's the same. We can basically create these concave and convex collision where it's the same objects in the same distance, but not the same effective distance. And look at that on the x-axis, the distance to collision, the real distance in pixels, okay, between them and people's ratings of causality. And you can see a very clear difference between concave and convex collisions for the same actual distance. And this line over here, these dots, over here are people's ratings, and the lines fitting through it is the computational model of approximations that we fit to this thing. And when I say fit to this, I mean that we just have a single parameter that is basically the kind of thing for how approximate these things are, okay? We fit that a single time, and then that predicts these things. We can do that for Michaud-ian launching. We can do that for time to collision, same model, okay? So you see an object about to hit another object, and you need to say, when will it hit it? Press the spacebar. And we can do that for change detection of things moving behind screens. These are all very well-validated experiments that we just repurpose for these things. And again, the same idea falls out of all of these, which is people's approximations are not perfectly shrink-wrapped around this. They are using approximations, and those approximations are not spheres nor cubes. There's something in between a convex hole and that thing. We use something called alpha shapes. I'm not going to claim that people are actually using alpha shapes. We just use that as like an off-the-shelf useful model that mathematicians have come up with for approximating bodies. We have students working on what we think is actually being implemented neurally here. Okay, transition. We're moving, as I said, I'm moving at a rapid clip to try to get the point is not specifically about approximate bodies. The point is about approximations in mental simulation and physics in general. So the next thing is about partial simulation. And I'm going to use this in two ways. Okay? I'm going to use this both to tell you about a particular study I think is cool, and about this more general notion of approximations. But also, I want to give a fair shake to people who think that nothing like this is going on. Okay? I keep saying, oh yeah, people use mental simulation, da da da. And I told you not everyone believes that. Okay? So let me try to give a shared fake to the opposition. And this is work led by all these people, obviously, but I want to shout out in particular Lonnie Bass over there, who was a postdoc in the lab at the time. So before I tell you about our solution, I need to tell you about the problem. Here's some really interesting work coming out of the lab of Neil Bramley and Ernie Davis and Todd Gorekis and things like that. And the idea is that they think, well, look, if people are using something like this game engine, this physics engine, this mental simulation, then it should obey the laws of probability, in the same way that reality has to obey the laws of probability. What if we could show that that's not true? So in reality, the conjunction of two events, A and B, the probability of that conjunction of these two events has to be equal to or smaller than the probability of a single event happening. Hopefully you all agree with that, okay? And if not, crack open a probability introductory textbook. But I'm sure this is all very intuitive, right? It has to be. This thing is contained within that kind of thing. Great. So what they did is they showed, I'm giving the game away, they showed that people don't seem to obey that. But people seem to show a physical, what's called conjunction fallacy, modeled on classic conjunction fallacies in cognitive science and behavior and decision-making in economics, and I'm sure a lot of you know it. They showed people these very simple physical scenes, animations. These animations were run on, it's kind of like iPad games. And here they asked people, look, there's going to be one of the events is, let's call it G, which is the sphere landing on the grass, G for grass. Okay. And another event is H for hit, for it's the probability of this cannonball, this gray cannonball hitting the sphere. And we can ask people, we can show them like lots of these different displays in lots of different ways and basically ask them to like rate the probability of these different events independently of one another. But then of course we also do, what is the probability of the gray thing hitting the pink thing and the pink thing landing on the grass, right? And when they do that, and they do it very carefully and very well, they find that people's ratings of the probability of both of these things happening in conjunction is greater than the probability of simply landing on the grass. Okay, so that's a violation of basic elementary probability. This is showing a physical conjunction fallacy. This is showing that people can't be using physics engines. They are dead. And the conjunction fallacy killed them, except wait a minute, right? Not so fast. Shout out to even older TV than that. One more thing, if you will. I started this whole talk by saying we're not using perfect simulators. Oh, I didn't start, but like somewhere early on, I said people aren't using perfect simulators, right? True, if the simulator was exactly a one-to-one veridical copy of reality, it couldn't disobey probability. But it's not, right? And there are many ways in which it's not. And one simple way in which it's not is the idea that people probably don't simulate everything in their environment right now. Even if I'm using something like a physical simulation to simulate me, you're probably not keeping track of everything. And again, something very simple to reason about, like maybe you're not thinking about moving that cannonball when you're being asked the question about whether this thing will hit the grass. You can then build a simple simulation that has only one parameter, that is just, will we move this other object, yes or no? For each branch here, it's elementary probability. You run the simulator and get the probability of will the thing land on the grass, and then combine them again. This is high school algebra to get that equation over there of the probability of the thing landing on the grass as a function of both the underlying physics and whether or not you moved all objects in the scene. Now again, I said I'm going through this relatively quickly, but please believe me when I say this is one of the reasons I'm very proud of this project for Lonnie and things like that is because we did not fit anything to data. We pre-register, we put all our cards on the table or all our marbles in one basket. I don't know what the right thing is. It's like we thought about this, we built the model, we made the predictions, we pre-registered everything. And the model makes these very specific predictions about what kind of conjunction fallacy you will see, okay? So the size and existence of this conjunction fallacy depending on how these objects start out, based on that very simple model that I showed you. And it gives this very non-obvious prediction of a U-shaped function that is modulated linearly based on the starting positions of these objects. So this is what the model predicts. Over here is like where the starting position is of these objects and how the trajectory is shaped. And on the y-axis, it's just like the size of the conjunction fallacy. If it's above 0, people are irrational. If it's below 0, they're obeying physics. And the size of that thing is how much they're violating it. Okay, so you can see again, we're predicting that sometimes it'll happen and sometimes it won't. And this is what participants should, right? right? And none of this was fit to that in post hoc. And you can do a correlation between these things. You can also do this for like other things within that simulation, other events, and what are the probabilities of things. And again, there's remarkable matching between the model and what participants have been doing. This doesn't negate Ludwin-Pieri and Gorekes, right? We did recover their results. They're over there, right? They're in that area of the parameter space. That we did replicate what they found, but we can explain why people are showing these errors and when they show these errors and how they're showing these errors from a very simple idea of partial simulation. Okay. Again, I warned you, I'm going to do a rapid transition. We have 2 more things to cover before we open it up to a general discussion. And now we're transitioning into this idea of like the connection between intuitive physics and imagery and imagination. So everything I've said so far is about intuitive physics, but I'm sure I've been relying a little bit, and I'm sure a lot of you have had this idea of like when I said that I'm going to throw this at you again, I'm not going to do it. Some of you who don't have aphantasia may have formed a visual mental image of what that looks like that we usually don't think of as intuitive physics. We think of that as, yeah, buddy, that's called the imagination. People have studied that. Look into it, which I did. So the idea there, people, by the way, know about like the imagery debate or things like, or, sorry, who here knows about the imagery debate? Great, okay. Who here doesn't know about the imagery debate? Okay. Who here has heard of aphantasia? Who here hasn't heard of it? Okay, so you know about aphantasia, but not the imagery debate. That's an interesting position to find ourselves in. All right. So let me walk you through the details of the study for a moment and then explain how I think it relates to the imagery debate and aphantasia and things like that. We'll start out actually with, before I tell you why we ran this and how it relates to it, we'll start out with a phenomena, an empirical bit of stage magic or whatever you want to call it. I'd like you to imagine the following scene as vividly as you can and hold it in your mind for a few seconds. Maybe you already started doing it. If so, sorry for doing double work. But please imagine a person walks into a room and knocks a ball off a table. Okay, hold that in your mind as vividly as you can. Who here has aphantasia? I'd expect 4% of you, but okay. Okay, now stop thinking about that for a second. Now, I have a question for you about that thing that you imagined. And please don't reimagine it to answer these questions, okay? I'm going to ask you about some properties of that scene, and you just need to answer, was that part of your scene or not? Did you bother thinking about it, yes or no? Okay, it's a yes or no question. All right, so let's start with, I'm going to say the property, and then I'm going to point to you, and then you just need to say yes or no. Okay, yes means that was part of my mental scene, no means that wasn't part of my mental scene is the task. Okay, the color of the ball. Okay, some of you are raising your hand. Not all of you are answering, so you need to answer yes or no. If it wasn't, you say no. Okay, so the color of the ball. Okay. The position of the ball relative to the person. The trajectory the ball took, like you can sketch it out with your hands. The hair color of the person. The color of the person. The size of the table. Okay, we can keep going. The size of the ball. Okay, we can keep going like this, right? And the point is that like for any property that we ask, these are properties that should be immediately obvious if you were to actually create this image in your mind's eye. If you had like a pixel-based representation or you saw this thing, you should be able to answer what was the color of the ball, no problem, right? And yet for any property that we asked, sorry, this is transitioning, oh, sorry. For any property that we asked, I'll explain why I'm showing that in just a second, some significant number of people said that wasn't part of my mental scene, okay? And those weren't randomly distributed. I'm sure you found for yourself that like color of the ball, unsurprisingly, was around like 50-50. Position of the person relative to the ball, most of you said it was part of it. Hair color of the person, whatever. This is an age-old question in philosophy and imagination and things like that. We call it non-commitment. It doesn't always go under that name. But the idea is something like, from philosophy, it's a question of perception. How can you know that this is a speckled hen without knowing how many speckles it has? This thing from Dennett about the purple cow, right? How can you imagine a purple cow and yet not know exactly what shade of purple it is? This is, by the way, one of the most famous nonsense poems from 150 years ago, now long forgotten, but I think it does say something interesting about the imagination and non-commitment. I never saw a purple cow, I never hoped to see one, but I can tell you anyhow, I'd rather see than be one. And this came up again also in the imagery debate, which was this major argument that's still ongoing and has been going on for decades between what is the format of mental imagery, okay? So if we think that you have some sort of thing in your head, some computation where you're creating these mental images, what is that format? Does it look like a pixel-based representation? Does it look like a logically based representation, like predicates, like language? If I'm going to build a machine to imagine, What should the format of that thing be? And the major argument there was between people who thought it was more like a picture or depictivist. I'm way oversimplifying. People who know the imagery debate, please don't yell at me yet. Two of the major camps within this are between people who thought that these were picture-like, pixel-based, and people who thought that these were more language of thought-based or things like that. And within that debate, a side note within that debate, but still very important, was, hey, I can imagine a striped tiger, but I don't know, I can't count its stripes. I don't know how many stripes it has. Okay, so in what sense is that an image? And see all these people for a lot of that debate. But it was mostly just dudes arguing with one another. Okay, like it seems to me. Well, it seems to me not. It's n equals 1 on both sides. Okay, and in both of these, they didn't really distinguish between which properties do you bother imagining and which do you not. They just said there are such ones, I think. So first of all, yes, there are such ones. We asked many, many, many people about the situation. And the point here is that just how much people reported that wasn't part of my mental representation for different kinds of properties that should be readily apparent in the actual scene. And again, the point is for every property, some people said they didn't commit to it, and it's not uniform. And it's interesting that these spatial physical properties are such that they seem to be more committed to, or more likely to be committed to, than the surface ones. We did this across many different scenes with a bunch of people, like it wasn't just the person and the ball, and for all of these, the same conclusion. It's the same conclusion, okay, which I just told you. It's not 0 for any property, and the properties don't seem to be randomly distributed. This doesn't seem to be about vividness, yes?
Someone's an artist versus this, or if someone has a lot of time, I'm just thinking something they honestly haven't.
Yes, so in general, I'm gonna rely on a few different things here. One is we didn't ask people what their profession was. We did try like different timings and things like that. And we were hoping to capture some notion of, if this is true, what I'm about to say about non-commitment being some dependent on a hierarchical model of when do you bother imagining certain things, then if we're able to stop that process quickly, you should be more committed to these things than the things that come lower down. We ran into issues with that. Turns out it's really hard to get people to stop imagining stuff, and it's maybe not surprising given what we know about the temporal aspect dynamics of the imagination. This usually you have a fully fleshed scene in about 200 milliseconds. It's very hard to cut that off. But in terms of artists, I'm gonna fall back on the fact that like even in aphantasia, you don't really see differences there. Like you can get aphantasic people who do animation and do, are architects. All the stuff that we think might have to depend on very rich mental images doesn't seem to be the case. But I'm happy to get more into that in the discussion, yes.
Is there kind of a threshold effect that as you go up, suddenly you say yes, then you are likely to say yes to all the other ones, or is kind of not correlated?
So they didn't seem correlated with one another. No.
About one person along that axis.
So sorry, that's not the right question for that. So you mean something like, let me make sure I understand the question before I give an answer evaded. You're saying something like, if a person said, I did think about the size of the bowl, I'm also more likely to say that I thought about that thing. I'm trying to remember if we ran something like that. I think the answer is no, but we should talk more about that. I understand that's a non-answer, but that's the best I have right now. No.
I didn't expect
Yeah.
Popped in my head. I did not do that, but I did.
I appreciate that. Please continue. This is just saying it doesn't really seem to matter for the vividness aspect, okay? So if people like say, look, I can really, really clearly see this image in my head, I have like hyperphantasia, it's like a movie, they might say, what was the color of the ball? I don't know, I didn't bother thinking about that. It didn't seem to be related to that, yes. To that or to the vividness? Okay, yeah.
So actually, anything like sometimes cultural experience can impact how people.
Yeah, so we looked at things, we looked at some very basic stuff like education, gender, age, things like that. That didn't seem to matter. I can't tell you that this isn't about cultural differences more broadly because we didn't have a culturally diverse enough sample to be able to answer that question. These were US adults. It was a representative sample of US adults, but US adults nevertheless, yes. But again, it doesn't seem to be about vividness. Some people like who have aphantasia will say like, look, I can't create mental images. I don't see anything. What was the color of the ball? Red, right? So that doesn't seem to be predictive of this non-commitment thing. It's like, it's a very, very weak correlation. It depends how you ask this. If you go out and you ask your friends this question, please be careful how you ask them. If you ask them, okay, so imagine I saw this talk, here we go. a person knocking a ball off a table. What was the color of the ball? They'll say red. Okay, if you ask them what was the clothes of the person, they'll say zip bag with this thing, right? The pragmatics really matter, and I think there's a lesson there for how we study the imagination, because the pragmatics of saying what was the color of the ball is, oh, you want a color, I'll give you a color, right? It's not, you need to have them be aware that they can say, I didn't think about it. And when you ask it that way, they'll basically say 100% to anything that you ask them about. And there's a lesson there, by the way, for like people's reasoning in general, I think, but in decision making. I think this can all be relatively well explained by this idea that people, again, the game engine idea is hierarchical and separates between physics and graphics. Those of you who've ever dealt with these kind of pieces of software, there's the underlying amodal spatial representation. If I were to capture this thing, I could create that thing without yet an image to go with it. It's a separate computational step to say, okay, now there's a camera over here. What does that scene look like from over here? Now there's a camera over here. What does it look like from over here? It's the same scene. I could use that scene to answer questions like, where is the mug? Or will the mug fall, or things like that. I don't have to render to answer that question. Okay, so we should separate out rendering from this spatial kind of thing. And I think once you start thinking about like hierarchical scene construction, a lot of that stuff comes out of it. I'm again going to go one last time with this apology. If that went by quickly, please come argue with me later. We also had a recent Trends in Cognitive Science exactly on that point. Okay, and we think that aphantasia is a broken rendering operation. And once you think about that, lots of mysteries and mental imagery seem to make sense. Okay. One last thing for you before we open up into general discussion. This is about capacity limits of mental simulation in general. So this is not about unlimited power. This is about limited power. The idea is that if you are able to simulate something in your mind, if you're able to run something like this kind of simulation, again, it has all kinds of approximations and hacks and things like that. But a principled one might be the amount of things that you can move in parallel, that you can update. Okay, so again, if you were to run something right now, this scene, or like 4,000 ninjas fighting with frisbees or whatever, that would slow down your computer relative to just one ninja. That's unsurprising, right? Again, there's these limits of how many things you can move and keep track of at the same time. So we were interested in like, what is that in the imagination? And I want to shout out like, decades of work in perceptual tracking. Obviously, people have noticed that we can't keep track of everything right in front of us right now. There's too many of you for me to keep track of perceptually. If you're a busy lifeguard, you can't keep track of everything. If you're juggling balls, it's difficult to keep track of. We know this in perception. And oversimplifying decades of work, there are limits on these things. Very roughly speaking, if you've never heard this before, the idea is something like you can keep track of about 3 or 4 objects moving independently in direct perception. Please don't tell my friends I said that, because of course it's not that simple. You can keep track of more or less depending on how they're moving and whether they are obeying physics and things like that. But for now, the fact is that this does seem to be some limit that is around 3 or 4, something like that. And the question is just very simple. How many things can people keep track of in their imagination? And how does it match with perception? How do you even study this? Well, let's do it right now. So I'm going to run this experiment on you as best I can. And I'd like you to please humor me. I'm going to show you this ball. And if it's going to move and fall and hit the ground. Okay, so this thing is like a collider. This is the grass. This is a ball. If you see anything on the left of this kind of metallic bar hitting the ground, I'd like you to take your hand and slap your left thigh when it hits the ground. Not yet, it didn't hit the ground just yet, but good practice, okay? So ready with your hands, ready with your thighs, okay? So when you see this, great, very good. And again, the simulations are a lot more smooth on my computer and things like that, okay? That was a warm-up, let's do one more warm-up. If you ever see a ball to the right of this berry hit the ground, I'd like you to stomp your right foot, okay? Everybody ready with their right foot? We're gonna try that. Here we go. Okay, clear, great. Cool, that was the warm-up. Now we're going to do that in imagination, okay? I'm going to show you a ball. I'm already telling you it's going to be on the left of the barrier, okay? So prepare your hand and your thigh, all right? And it's going to pause. And I'd like you to continue it in your mind's eye. And when it hits the ground in your mind's eye, the mind's ground and mind's eye or whatever, I'd like you to slap your thigh. Is that clear? Okay, here we go. Okay, great. So, very good. We could do that with people. We didn't do slappy stompy. We did like actual controlled psychophysics. And when you do controlled psychophysics, people are pretty good at this kind of thing. And when I say pretty good, I mean they respond linearly to the changes in the ground truth and things like that. And there are individual differences here that are interesting but not important for this thing. The point is, like, tracking is pretty good when it comes to this. And now you can imagine building a different model for how this kind of capacity limit would work, right? Imagine that you had like the ability to move multiple things in parallel. Like you have multiple cores in your computer, and you can task each core with moving or updating or simulating each one of these things. So I don't know about you, I have 16 cores in my computer. You probably have more. But the point is, if you have 2 for this thing, you can just move these things independently. But imagine you only had 1 core, okay? So if you had only 1, you might need to first of all move this thing, and then go and move this other thing, right? This leads to very different predictions about people's reaction time, and how their reaction time should look like relative to the ground truth for the first bowl versus the second bowl. Obviously, there's going to be some reaction time differences there. So which is it? Okay, well, let's try that on you, okay? I'm going to show you now 2 objects moving in the imagination. The task is the same as before. When the one on the left hits the ground, and it might be before, it might be after, slap your thigh. When the one on the right hits the ground, stomp your foot, except these are both in the imagination. Are people ready? Okay. Are people ready? Okay, thank you, appreciate that. Here we go, okay. That was one thing and kind of choppy. Let's try that again. Here we go. So again, trust me, it runs very smoothly, like when you actually show people these things. But the point is, we can run this with people across many different situations and things like that. Which one of these 2 is it? Which one of these 2 models? This is for the first bowl. It doesn't differ that much from tracking just one thing in isolation. You don't seem to be paying a cost for the fact that you're tracking 2 things, okay? And the second one is, as I gathered from the giggles that were in this room, the second one shows this very large serial gap. It is very well fit by this computational model that moves things in serial rather than in parallel. Now, were there individual differences? The short answer is not as far as we can tell. Right? You might think like, you know, shout out to those people who can only move 1, I'm different, right? I can move 2, no. It doesn't seem to be the case. Everyone that we checked was limited by this kind of thing. Is this about a motor bottleneck? Maybe I can simulate things perfectly fine, but you know, when I'm trying to coordinate like slapping and stomping and like it's a motor issue. That's where the bottleneck is. I can simulate things just fine. It's a different lower level bottleneck. We tried a bunch of experiments to rule that out, and as far as I know, we did rule that out. The idea is we just show people these things in direct perception. If this is the image you saw in your mind, and the problem is a lower level bottleneck, you should then see the serial gap for perception, which you absolutely do not. It seems to be much more like something in parallel. We tried many different follow-ups. Is this about motivation? Is this about physics? Is this about grouping? There's like 9 different follow-ups. I encourage you to read the paper. The bottom line for all these things is, how many objects can we simulate in our imagination at once? 1. Yeah, yes.
Is there any difference if you like split the vision down the middle and look at one ball with one eye and one with the other?
Great, I love it. And I have a guess for why you're asking this, but do you want to say why you're asking this? Or, oh, no, you don't. Okay, interesting. So you've stumbled on a very interesting, sorry, not stumbled on. You've asked a very astute question, but part of the reason why it's an astute question is because with perceptual tracking as well, there's evidence that it's possible that different parts of our brain, the capacity limit of 3 or 4 might be actually more like 1 and 2 here and 1 and 2 here, or something like that. That's speculative, but there's like earlier evidence with people who have like split brains or things like that. So the answer is I'm not sure. We didn't do that, but it's interesting. I see some more hands up, but if you'll allow me just briefly, we're nearing the end of it, and then we can just open it up in general, because look where we are. We did it. We made it to the end, okay? So in summary, I'm interested in intuitive physics. I'm interested in intuitive psychology. I'm interested in the computational models that people are running to try and arrive at these answers. Everything I told you today could be applied to intuitive psychology as well. How do people do it? What approximations are they doing? Within intuitive physics, the mental game engine representation has been particularly useful, I think. Please understand it's not the only game in town, and I don't think it's the only thing that people are using to understand intuitive physics. I don't think that. I just think it's one of the things that they're using. And then it's really interesting to ask what kind of mental simulation that is. What sort of approximations do people use? I've shown you some examples of that and how it connects to imagery and imagination and things like that, and lazy evaluation. and also more broadly to simulation in this way. And the key takeaway from that part is simulation is not the same thing as rendering. And with that, I will stop. Yeah, so sorry to have cut you off if that was.
For the bouncing ball where you were trying to figure out if it's a sequential process or potentially parallel, do you notice a learning effect?
No, so we looked at that. People have seen some, they get very, so yes, I only showed you two things here. You might think maybe people just get better over time. We didn't see a learning effect despite dozens and dozens of trials in what we did. People were the same at the beginning, at the end. That's not to say that I don't think that you might see learning in general in intuitive physics. Of course you will, but and you might think like, look, I can juggle. Like juggling is more than one object. What are you talking about, right? I don't know if that's exactly what. So sorry, I'm slightly moving the question this way. If that is the point, then AI would say, well, that's perception when you're juggling. But also what's happening when you're learning in a lot of these things, in perception at least, is that you seem to be moving it from one kind of representation to another kind of representation. Like when you're learning to drive, right? You need to keep track of a lot of different things. You then seem to be moving into a different format. So even if we were to find after a bazillion trials some kind of learning effect, that would be interesting. But I would say maybe at that point, they're not even simulating anymore. They might have moved it to a different representation that then could potentially be run in parallel.
That was such a good talk. I'm curious about your thoughts on the models that we have today, Sora and VO3 and everything. It looks like we have game engines that can do these simulations well. People learn, we do trial and error, and we learn these things. These models have a lot of data, but what is it that they're kind of missing that leads them to be not very good at
yes
simulations and videos? And I'm curious about
excellent question. Outstanding question in two ways, like good, but also outstanding in the sense that it's not a solved thing. So I'm just giving you my views. I think this is a topic for massive arguments. I was just talking yesterday to the head of the head of Sora at OpenAI, like we argued about some of this stuff. So it's still relevant in that sense. Before I answer that, I want to just differentiate that when I say, what you said, we have game engines that can do this, so what's missing or something like that. I want to just differentiate the stuff that is like Sora and VO3 and things like that, they're not using game engines. They're taking a model, they're feeding it a gigantic diet of videos. It's learning something, we're not sure what, and it's producing videos. To the degree that it works well, you can then make two claims. You could make that like, and we could argue about whether it works well or not. To the degree that it works well, you might say, well, it seems like it learned a game engine. Somewhere in there, in the weights, it has learned this thing that you are talking about. Or maybe people don't need a game engine. One of these two things is probably right if it works well. But it doesn't work well. And I think part of the reason it doesn't work well is because it hasn't learned a game engine. So when you're asking me what's missing, I think it's exactly missing that kind of representation. And what that representation allows you is, by the way, these game engine representations don't need massive amounts of training and data. They work out of the box. And that's upsetting for a lot of computer scientists because you get brownie points in computer science these days by assuming as little as possible. And it's anathema to like say, well, here's a way of passing this task. I just build something in that can pass it. And they're like, well, that's cheating. And I'm like, well, that's humans. Like, so anyway, it's an ongoing argument.
Appreciate your talk. So regarding the hierarchical scene construction, you already said there is no correlation between maybe some of the variables, but did you also observe there is a repeating patterns for individual level? Like people probably emphasize some part, and you can in your experiment, could you observe such patterns? Because maybe some people more empathize, and then that could also imply that it's related to some of the values that those people appreciate.
Sorry. Yeah. So several different questions there rolled into. So I just want to make sure that I address them. Just to be clear, by the way, like when we looked at these different properties, you do see, generally speaking, that spatial and physical properties are the kind that people are more likely to commit to, generally speaking. and the kind that we would call surface level, like texture, color, things like that, or the kind that they're less likely to commit to. And we tried this in many different ways, and we tried this in many different scenarios. We tried this, by the way, for also, I'll get to the question in just a second. I'm just, spoiler alert for ongoing work, we also tried this with like very abstract scenes for various reasons. Like we told people to imagine something falling on something. Intentionally, you're supposed to like maybe or maybe not fill that in, and people seem to be filling that in a particular way that is relevant to this. We didn't see individual differences so much. Like, I mean, you see individual differences in commitment in general in the sense that like there is, if you take like, let's say there's 10 properties we ask people about. It's not that everyone committed to 7. There's some Gaussian around 7. Some people had more and some people had less. And maybe this gets also to the question that we had before, where like there is a probability of like the ones who said less were still likely to commit to the spatial physical stuff. So there's individual differences in the sense of that Gaussian, but it's not a very wide Gaussian, and it didn't seem to correlate with the stuff that you might expect it to correlate with, like vividness or like aphantasia. We didn't, depends what you mean by individual differences. We didn't ask people a lot of questions that would allow us to, like what individual differences did you have in mind, for example? Oh, you said empathy, that was one of them, yeah.
I would say like for abstract level, like I think Ullman also mentioned there can be some cultural variance. So like
yes, yeah. So at least 2 different things that we didn't test for. One is, for example, amount of empathy or something like that, and another one is something like cultural differences. If we try this within one specific U.S. culture or a different culture somewhere else, the short answer is no. No, we didn't look for that. Not no, there weren't differences. This was mostly to do with like the way our IRB is set up and that prefers US participants and things like that. I'm willing to bet you at least $7 we don't find major differences for these things. Like to the degree that what I think here is true, I think it also is a claim about like, these are pretty basic processes along the lines of perception, things like that. We wouldn't expect you to see this as bigger or smaller if you're from a different culture or more apathetic or things like that. So my money, I'll bet you $8 there isn't a major difference there. Sorry, I wasn't keeping track too much of.
So I have following on the previous question about the game engine. So like modern simulators like Majoko, ExactGym, or even Unity 3D uses like simpler physics models than the real world. So I'm wondering such a gap between the simulator and the real world, will it like influence people's perception or imagination about this physics?
Okay, that's great. I just want to make sure I understand. When you say imagination, for example, what do you have in mind?
So it's just like when the ball will hit the ground or something, the result in the simulation may be different from the result in reality.
Yes. So the short answer is yes. These simulators don't have perfect physics. They're not simulating things at a molecular level, and they're also not solving Newtonian equations and things like that. To the degree that people are like these simulators, can we find differences between what people are predicting and what the reality is that is more in line with these engines than these things are? The short answer is yes. I know there's a hard stop at 1, so maybe we can talk about that later. There are, I see some of these, by the way, as kind of being about some of those errors as well. There are other kinds of errors similar to those that have to do with people's not quite understanding forces and simplifications of forces, is maybe a simple way of putting it. I'm going to just say one thing that you said about the imagination, which wasn't exactly a question, but to the degree that this thing is right, one of the things that I love about common sense reasoning and these kind of models is that you can also start to think about common sense reasoning in uncommon situations, in the imagination, in magical situations and things like that. And in some work that I didn't have time to talk about, we asked people variations on things like, suppose that there's a magical world where wizards can cast spells and things like that. What do you think requires more magic juice, effort, mana points, whatever it is you want to call it? You can try it right here. Like, do you think it's harder to make a frog conjured up from existence, like appear from the ether, or change its color from green to purple? Who thinks the harder thing is changing it from green to purple? Who thinks it's conjuring it up from existence? Okay, great. You're all like our participants and things like that. Now, why a perfectly reasonable answer is to say, none of these are possible. These are wizards. What are you talking about? This is like a magical world and things like that. And yet we have intuitions about these magical worlds. We tried many different violations, and they seem to track this kind of hierarchy, which is also, by the way, seems to track like the acquisition of these things in core knowledge as well. Like very early things like permanence seem more effortful or something like that. And incidental properties like color, that's low down. Yeah. Okay. With that, I think we're, well, sorry, someone else should call the hard stop, I guess, but.
Do we want to have one last question and then? Yeah. Any questions?
I'm happy to keep answering stuff. I was just told I need to finish by 1, that's all.
Yeah, sorry, I want to go back to individual differences, not so much as group differences, but I just wonder if it's interesting at all to look at individual differences and it's predictive to other important outcomes, because I think in the area of computational modeling of decision making, it's always important that's predictive of some future important outcomes, right? I wonder if it's the case here, or is it not important or interesting at all?
So let's separate that out in a few different ways, right? These models are predictive in the sense that I can take them and predict what people will do in new situations.
To the individual level.
Well, to some degree, individual levels as well. For example, when we took the probability of someone simulating things in the second example, this one over here, partial simulation example, that was predictive across trials between individuals, for example.
Yeah.
I confess, this is a tongue-in-cheek thing that I'm going to say in just a second, so just please understand that I don't mean anything by it. I'm not that interested in individual differences, but maybe that's just me. Right.
Would it be interesting at all?
That was a joke.
Yeah.
So I agree with you that individual differences might be interesting to the degree that they are predictive, but these models are predictive of what people will do in new situations, in the sense that I can take this and then generalize to new scenes and say what people will do in these new scenes. You're right that it would be ideal if I could predict what person A will do in that situation, but most of the properties we're looking at don't show that variation or are not the kind of things that we've looked at. And again, I point you to the idea that, like, are there individual differences in perception? For the most basic level processes, I don't think there are major differences.
What about like people with special needs, like autistic people?
Yes. So we haven't tried that for the intuitive physics side. I have some work on that for the intuitive psychology side, where I think it might play a role, but it turns out to not actually play as big a role for some of these mental state attributions. The kind of intuitive theory of intuitive psychology is that, and this was much more popular in the 80s, was that ASD is primarily a deficit in something like mental state attributions, that these people don't understand theory of mind or something like that. We've moved way past that. Like, that doesn't seem to be right. So the degree that intuitive psychology at the heart of it is about this kind of basic level understanding, I don't think that we would find major differences.
That's great to know, yeah.
Yeah. There are differences, by the way. This is not my work. You should look it up. By beautiful work by Kelsey Allen, who's a major person in intuitive physics, about people's ability to reason about new tools, create tools and things like that based on their own differences. So for example, people who were either born with or lost their arm or things like that, does matter for how they then adapt to different intuitive physical situations in a way that is still predicted by a general game engine kind of thing, but does show individual differences there in the way that you might expect. So Kelsey Allen, tool use, PNAS 2021.
Great, thank you.
Any other, yeah, Ullman.
Perfect.
Yeah. So a lot of your work is focused on human perspective, but I can imagine a lot of animals, they have different visual reasoning. So have you think about a way to like simulate how different animal is like do those kind of reasoning, and then how it will relate to evolution and like make people stand out in these like millions of years? Yeah.
Yeah, so good question. I'm not an animal researcher myself. Everything that I'm saying right now is based on stuff that I've talked to colleagues about and things like that. So I said at the beginning when I talked about core knowledge and things like that, that it is shared with other animals and that there are normative reasons to expect that and empirical data to back that up. Normative because this stuff is useful not for our current society. This stuff is useful for creatures living on planet Earth with other creatures, right? Like intuitive psychology in the sense of mental state attribution is useful for a wolf. Understanding how things move around and crash and fall down is useful for a lemur. And to the degree that people have run experiments on intuitive physics and intuitive psychology, there is definitely a shared understanding between, understanding is not quite the right way of putting it, but there seems to be a lot of shared representations in this way. So if the thing that is driving intuitive physics in people is something like this mental simulation, then the claim would be that this exists in other animals as well. There's been some interesting work on that in non-human primates, for example, that seems to conclude that non-human primates are doing something like a mental simulation as well. I'm bad with names. It's someone at MIT, and if you'll give me a second, I can pull it up. But some people have been looking at that. Some people more recently at Northeastern have been looking at basically the physics engine in rats, for example, and things like that. It's a very much an ongoing topic of study, but yeah. The claim at least would be that this would apply to to a lot of other animals, not most, definitely not most.
I think we have time for one more question. We have multiple people who have questions, so.
Great. Thank you for a great talk. I'm curious, you talked about wanting to look at babies or children all the way to adults. The types of computational models you're building, can they also address learning or development, or do you sort of have to fit them to different age groups?
Yes, so the short answer is yes, and I can point you to some relevant papers. We've done learning things like take the notion of a game engine, a hierarchical game engine, and think of learning as basically learning at different levels of this hierarchy. Like I generally assume that the world works according to Unity or Unreal or whatever. That defines a bazillion different games. Maybe in this particular game, things that are red are heavy or something like that. Like you can definitely, that's very low down the hierarchy, but you can build a learning model that has these kind of assumptions and does learning there. The kind of stuff that relates to babies is less about the learning in babies, although we have some stuff on that. I'd point you to something that I think is very interesting, work led by Kevin Smith, this thing called ADEPT, where we took the kind of things that babies are surprised by. Do we have that here? Anyway, do you remember the image of the baby being surprised, right? Like classic stuff that has been established empirically in development of this is the stuff that babies find surprising in intuitive physics and the kind of stuff that they don't find surprising. So you set that up as a test for computational models. The computational models watch these videos and need to say, basically give a prediction error or a probability distribution, which one of these videos is more surprising or things like that. And then we can compare several different models. One model is a model that's much more like a, off-the-shelf encoder, decoder, GAN with neural Turing stuff, what they're calling off-the-shelf these days, but like something that doesn't know about physics. You can compare that to something that we're considering like a minimal game engine. So something that just has approximate bodies and approximate physics of things moving around and some memory in the form of like a particle, what's it called? A particle filter. If you assume that, if you give me that, which I would say is a pretty bare bones physics engine, it passes all of these things in a generalizable way. Where the learning comes in is it needs to learn to see. So the vision model needs to be trained up, not the physics model. It needs to basically go from pixels to game state, right? To be able to like sort of look at this undifferentiated blob of pixels and say, there's an object here and there's an object there. And I think this is the approximation for this thing. So there's learning happening there, but less so in the physics for that part, if that makes sense. And again, you can compare that to off-the-shelf deep learning models that don't do as well, or do well if you train them on the standard 80-20 split, but don't generalize or things like that. So anyway, it's an ongoing argument.
Okay, if there are more questions, please feel free to come to the front and ask. And we'll see you all next week.
I won't, but have fun.